Yeah? I can. It works? Okay. Yeah. Hey, where can I check the time? Is there like a clock or so? Okay. Okay, okay, cool. Okay, all right. Thanks very much, Fabrice and Mark, for the invitation to give these lectures today. Yeah. I'm gonna really talk about a very recent topic. Maybe you've all heard about magic bilayer graphene, which is a new topic which is kind of developing since 1.5 years only. And I'm gonna basically try to summarize the experimental work which has been done in the last 1.5 years. That being said, there are really not too many papers out there, so maybe it's a total of 10 papers which has been published in the last 1.5 years on this topic. So I'm going to try to summarize all of that. And because I'm an experimentalist, I'm going to concentrate only mostly on the experimental part of the story. And next week, Leon Balance is going to be here, who's going to actually go hardcore into the theory of this. So I'm really just probably the foreplay for that, and I'm just going to really just talk about some experimental results. Okay, so the whole story is going to be around that. Okay, so that's a picture which we like to show. And it's basically sort of so-called twistronics, which is a new concept in quantum metaphysics, which allows you to, I'll do it again, allows you to basically twist two-dimensional materials one on top of another. And as you can see, it creates a sort of periodic superpotential on top of the intrinsic lattice of this whole thing. Okay, so the story really started only last year, when in March, Pablo Herrero from MIT exploded the bomb. He published 2 side-by-side Nature papers. It was also a big splash at the APS meeting in Boston. And basically what he reported were first, he reported on correlated insulator states in so-called magic angle bilayer graphene, which at that point was a new term, so nobody knew what that actually means. And then he also, in a side-by-side paper, he reported on unconventional superconductivity in the same system. Okay, so and ever since, basically, this has been a very hot field. So for example, it got selected as the Physics World's Breakthrough of the Year. I think just to go by the media news, I just want to emphasize why it was selected Breakthrough of the Year. And it was selected because it was shown by Pablo that the phenomenology is similar to high-temperature superconductors, basically similar to superconductors like the cuprates, for example. And that being so, the reason why this comparison was made is because the phase diagram of twisted bilayer graphene looked extremely similar to what we observed in cuprates. So in cuprates, usually we have a doping-dependent phase diagram where at 0 doping, we observe an antiferromagnetic phase. And then upon doping to the hole or electron side, one can basically make the system conducting, and one can tune into dome-shaped superconducting phases. And actually, a very similar thing we observe in graphene. So this is the phase diagram in graphene. And as you can see, also as a function of temperature and carrier density is basically doping levels, it was reported that there is a Mott-like insulating state around half filling of the Moiré band structure. And then if you tune slightly to the electron side or to the hole side, also superconducting regions appear, and these superconducting regions are also dome-shaped. And of course, immediately there was a lot of excitement because people immediately started comparing those two systems. And naively, the idea is that potentially the mechanism governing the superconductivity in those systems is actually similar. And I'll touch base on that where the discussion went from there on, because this is, of course, a highly debated topic right now. Okay, the other thing is, which one can also say, besides the band structure, is that actually the energy scales which are underlying this superconducting phase are extremely high. And basically, if one puts the superconducting state in twisted bilayer graphene in this so-called Moiré plot, where one can look at the, which is plotted as a function of Fermi temperature and Tc. So basically, this is a plot which compares Tc and the Fermi temperature at which it appears. We can note the following thing. So first of all, twisted bilayer graphene is here. So as you can see on that Fermi temperature scale, it's to the furthest left. So it is, by now, the superconductor with a proven record low carrier density. So Fermi temperature of any superconductor is basically the lowest in bilayer graphene. And the Fermi temperature, so the carrier density is basically almost 3 orders of magnitude lower than, for example, in the cuprates again. At the same time, Tc is not terribly low. So at the same time, Tc is 1.7 Kelvin. Again, it's quite low compared to the cuprates, which are have TCs up to 150 Kelvin. But again, comparing it to the Fermi temperature, this number is not so bad. And basically, what this Moiré plot tells you is that basically the closer on this diagonal line you are to Tc equal to Tf, so the closer you are in that direction to that solid line, the stronger the coupling of the underlying superconductor is. And as you can see, so magic angle bilayer graphene is basically on that energy, on those energy scales, is basically close to all the high temperature superconductors we know. So here, for example, we have the cuprates, and if you can see here, magic angle graphene is actually even closer to this diagonal line than these superconductors. Okay, so but that is really just the beginning of the story. So immediately, people have started to try to understand what could be the potential advantages of studying such a superconducting phase. And the advantages are the following. So first of all, graphene is ultra clean. So as I have shown before, it's a carbon-only material. So we have only one element which is making up this material. It's only carbon atoms. And that also leads to ultra-high mobilities. As we know from previous graphene research, single-layer graphene can have electronic mobilities up to per million. So it has extremely high intrinsic electronic quality. And for example, in this system, we can already readily observe quantum magneto oscillations, and we can make up the Fermi surface. The second advantage is that graphene is highly tunable. So for example, the cuprates, you need to, in order to study the phase diagram, you need to grow a lot of different crystals with a lot of different doping levels. And in graphene, because it's quasi two-dimensional, we can just apply an electric field effect. We can just apply a transverse electric field which penetrates it. And because graphene is thinner than the dielectric screen, the screening of its electrons, we can just basically apply an electric field and modulate its electron density. And for this reason, we can obtain phase diagrams in one single shot in one device just by tuning the electric field across it. We don't need to grow different crystal species, et cetera, and measure them all separately. And last but not least, it was developed over the last 10 years that we can readily integrate graphene into heterostructures, such as these van der Waals heterostructures, and I'll talk a little bit more about it next. And basically, we can manipulate it by hybridizing it with other materials and to really control its intrinsic energy scales by proximity effects and so on. Okay, and that just to contrast these properties with cuprates, for example. So as I said, graphene is carbon only. So it's really just one element. So compared to the cuprates, for example, right? So you have very complicated unit cells with many different atoms and so on. So this is about the high tunability. So this is a typical phase diagram one obtains with YBCO again. And as you can see, basically every data point here is one different crystal. So one needed to grow, I would say, 20 to 50 different crystals just to obtain a phase diagram like that. In graphene, you can do it all in one device. And heterostructures, yes, one can grow heterostructures with the cuprates, but I think with these MBE-grown heterostructures, it took really almost 20 years to make samples like this. And I think with graphene, we already can make these heterostructures starting now. Okay, so That is one of the advantages, and the other advantage, which I think is really exciting, and which has nothing to do with the unconventional superconductivity part, is that really in the last year or so, a lot of other phases were discovered in twisted bilayer graphene. So as I mentioned, we have the correlated insulators, we have the superconductors, then recently a strange metal phase was also reported in graphene. Then just a couple of weeks ago, another paper by the Stanford group was published, which observes magnetism in the very same compound, and topological states were also just reported a couple of weeks ago. So in principle, it's to me, even besides this unconventional superconductivity story, this system appears to be extremely rich, where a lot of different phases can be basically approached in a very tunable way, just by slightly twisting the layers one on top of another, or just by applying electric fields and gating the system from one phase to another. Okay, so this was just sort of the traditional introduction we make in this field these days. So okay, so this is just an introduction why we think this field is interesting. But so I want to go a little bit more to the bottom of it and really to explain how these, what this magic angle means, what these capabilities are. And I will start basically by giving you first an introduction on graphene and 2D materials. So this will this has nothing to do with twisted bilayer graphene itself, but it has to do with the last 10 years of the development of 2D materials and graphene in particular. Then I will explain why this magic angle is so special and why we get all these interesting phases at this angle. I will explain how we make the devices. And last but not least, I will basically summarize the recent experimental results on the correlated states and the superconductivity. And then, of course, so I will give another lecture on Thursday, I think. Then I will talk about the more of the recent trends like magnetism and topology. And next week, Leon Balance, I think he has 2 or 3 lectures. So he will basically put all of this in a proper theoretical context. Okay, so I'll start with graphene. I don't know how many people of you have studied graphene or studying graphene, so I'll just go really slow in the beginning. So, so graphene is really just this 2-dimensional sheet of carbon atoms, which forms a hexagonal lattice. And basically, the discovery of graphene was done with a Scotch tape trick. So people in Manchester, Andre Game and Kostya Novoselov, they were just playing with Scotch tape and graphite, and they realized that by just reapplying the Scotch tape to graphite, they can thin it down infinitely, down to one single layer. Okay, so and this was all done in ambient conditions, in air, really just with somebody having Scotch tape at hand and really a piece of graphite. So anybody of you can also do it within like, after a couple of hours training. You can extract a single layer graphene. Okay, so, and I think just conceptually, this was a very unexpected discovery that you can extract 2-dimensional materials just like that. But the other sort of immediate surprise was how good the crystallographic quality is. So because in principle, I think you can imagine that you can make stuff thinner and thinner, and then probably you would imagine that it just becomes very disordered and amorphous and bad, etc. But in graphene, it was not the case because it has this ultra-strong carbon lattice. The crystallographic quality is extremely good, and you can actually get single crystal flakes with almost no defects over tens of micron scales, etc. So, so it's extremely high quality. Okay, so and another surprise was that actually when people started looking at the band structure, they realized that electrons in graphene behave like massless Dirac electrons. So the band dispersion is linear. So really, electrons behave like they have no mass at all. They behave like photons or neutrinos, etc. And all of these sort of attributes of graphene led then in 2010 to the Nobel Prize. And of course, along the way, people also discovered many, many other things. So for example, I think these are listed all the records graphene holds. So you know, it's the stiffest material, it's the most stretchable material, it has record thermal conductivity at room temperature, it has the highest current density at room temperature, it has the highest intrinsic mobility at room temperature, etc. So all of the sort of attributes up to this date those are records which graphene holds. So, but of course, if you look at van der Waals materials, so basically like graphite materials which consist out of stacked two-dimensional layers, people immediately started adopting this trick to other materials. So we immediately discovered that in 2010, for example, hexagonal boron nitride was discovered. It's basically the analog of graphene, but with boron and nitride atoms. And this is, for example, an insulator. And you can prepare it in the same way. Then you can prepare MOS2, which is a two-dimensional semiconductor, the same way. You have black phosphorus, etc., which is also a semiconductor. And recently, there was a lot of interest in two-dimensional superconductors. So you can make, for example, BISCO or name the selenide also in the two-dimensional limit. You can make magnets in the two-dimensional limit. So you can basically name whatever condensed matter property you want. And you will most likely find a van der Waals material which you can fin down to the ultimate two-dimensional limit. And most of these single layers of two-dimensional materials are of high crystalline quality. So this is, for example, a picture not of graphene, but of MOS2. So you also find extremely large single crystals with pretty high mobilities. You can furthermore make layer number control of these devices. So basically, if you take a single layer of material or a bilayer or a trilayer or quadruple layer, it will always have a different band structure. It will always have some sort of a different electronic dispersion relation. So this is just an example. So this is single layer graphene. It has this linear dispersion relation. This is bilayer graphene, so two layers of graphene on top of another. It has this hyperbolic dispersion relation. In principle, the same argument holds true for most materials, where really, depending on layer number, you get a completely different system. Furthermore, you have enhanced electronic interactions, because usually these materials, they're just two-dimensional, so the dielectric screening, so they're not embedded in three-dimensional materials, so the dielectric screening is reduced. And of course, because of its two-dimensionality, you can strongly manipulate these materials by applying electrical and magnetic fields. So you can completely tune the Fermi energy with electric fields, and you can also, because of its two-dimensionality, you can apply a B field and really create distinct Landau levels in the system. Okay, and if this would not be it, the other thing which people quickly realized is that with very similar tricks, at which graphene is created, you can actually go way beyond it, and you can make heterostructures of artificial atoms, of artificial combinations. So basically, you can now first create those two-dimensional materials, but you can actually stack them one on top of another, like is demonstrated here, and you can create hybrid systems where basically you choose all the different combinations you like, you assemble them one on top of another, and you can basically create an artificial designer material which combines all of the different properties of the inherent two-dimensional layers. And this is done, this stacking is done also with a very simple technique. Again, this was all done originally in air. And basically with a polymer stamp, you can, usually we exfoliate materials on a silicon oxide chip. And then we find, for example, a graphene layer like that. And then we can just bring it into contact with another two-dimensional material, which we found, and we can pick it up. So if we bring, with this polymer stamp, if we bring HBN, for example, in contact with graphene, and we lift it off, the graphene usually sticks to the HBN. And as you can see, you end up on the stamp, you end up with graphene on HBN, and then you can continue this trick as many times as you want, and you can actually, like here, you can here create a triple layer of BN, graphene BN. But in principle, of course, there's no limit to this trick. You can basically build up 50 layers if you want, if you have the patience. Okay, so and the surprising thing is, actually, again, as with the discovery of graphene, this is a very simple, conceptually simple principle. And I think when we started doing this a couple of years ago, we thought nothing would work. And then again, the surprise was that actually the quality of so obtained heterostructures is extremely good. So here is, for example, a transmission electron microscope cross-section along basically a device like this, where Here, HBN, graphene, MOS2, another layer of HBN are shown. And as you can see, the interfaces are extremely clean. Okay, so you don't get anything amorphous, you don't get anything dirty, but you really find regions where these interfaces are extremely clean, and then the hybridization between the layers is extremely, extremely good. So as you can see here, for example, between graphene and HBN, it's a relatively large region where you don't find a single defect. You don't find a single impurity at the interface. Okay, so, and last but not least, of course, because of the type of assembly we use here, one other thing is possible, which is not possible, for example, in NB-grown heterostructures. You can actually rotate the layers with, with a random degree of freedom, depending in relation to one another. So imagine if you grow MB heterostructures. Usually you sprinkle atoms on a given crystallographic surface, and the sprinkled atoms, they have to adopt the underlying crystallographic orientation of the parent substrate. So you cannot grow a heterostructure with a random angle in between. But because we do this sort of assembly starting from two-dimensional layers, we can actually twist these orientations as we like, and we can basically create this, as I mentioned before, we can create this Moiré superlattices, which further renormalize the underlying electronic structure. Okay, so and basically this is where the field is right now. So I think since a couple of years, this was the main direction in two-dimensional materials and van der Waals heterostructures, is that people were looking at all of these degrees of freedom to create these designer materials. So you can choose, for example, superconductors, ferromagnets, Dirac and Weyl materials. You can apply gates between them. You can apply electric fields across them. You can furthermore rotate them at any angle as you like. And as you can see, of course, just from a triple stack like this, you already have almost an infinite phase space of materials and material properties which you can study. Okay, so this is where the field is right now. So now I just wanted to go over and really start from single layer graphene to explain now how the magic angle rises. So if there are any questions about this part, you can ask me now, or I'll move on to graphene. Yeah. 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 No. It's still. Yeah. This question comes since 15 years. Every year. Yeah. It's still Scotch tape, and for example, this PDMS stamp. It's basically the same polymer which you have in your plastic bag in the supermarket. You know, so it's. That's right. So it's really just like you just. I will explain later, but you really just put one of the layers on a rotational stage, which you can buy at any sort of. Basically, any rotational stage which you buy for scientific instruments like control labs, etc., it is good enough to control 0.1 degrees angle. But then that you actually get there, it's a lot of practice. But 0.1 degree rotational stage is not such a big trick. So all of this is really people are always surprised that this actually any of this works. Starting with the Scotch tape.
I think that needs to be really emphasized.
Yeah.
I mean, we are now almost
right.
7 or 8 years since the beginning of the graphene flagship.
Flagship.
So there are billions of euros that are invested
Yeah.
into this material, and the best
Yeah.
graphene that you get is still the good old Scotch tape.
Yeah.
So it's money that's perfectly thrown out of the window. This is something for future decision makers in science, politics, and important things.
Going to be more flagships, as I heard, right?
Pardon?
They're going to be more flagships.
Yeah, and they don't learn from the Euros.
Yeah. So since 15 years, people develop grow techniques for all of these materials, etc. And actually, for some industrial applications where you actually need large area graphene, etc., of course, this would never work. But for scientific purposes, still the best quality structures we can get are still from Scotch tape and PDMS stamping, and it's basically for 10 or 15 years, this is an alteration of the very same. Okay, so I'll just quickly explain a little bit more graphene itself. So graphene is basically a very simple system, which is really easy to understand. So graphene sheet really forms this hexagonal lattice, where basically you have 2 atoms per unit cell, which basically are equivalent. We call them the A and B lattice sites. And basically, all of the band structure you need to know here has to do with lattice hopping term, with this lattice hopping term, which determines the hopping probability between A and B lattice sites. And if you write down the Hamiltonian and calculate the time binding calculation, everything becomes very simple, and you get basically this type of band structure, where we have the Fermi energy sitting here at these Dirac cones. So we really, if we zoom in on any of these points in the K-space, we can get 6 Dirac cones, basically corresponding to K prime and K lattice sites. And basically, all of the transport properties are usually derived from the single particle band structure. So usually in single layer graphene, we can ignore all of the interactions. And we really can zoom in into these sort of linear dispersion relation in this hexagonal Brillouin zone. And the K and K prime points, we also call them 2 different valleys. So in principle, graphene is a 4-fold degenerate system. So you have spin up and spin down, and you have K and K prime valley. So usually, to fill up graphene band structure, you need 4 electrons to fill per unit cell. Okay, so this is single layer graphene, but then there is also more. So basically, you can also have AB bilayer graphene. So as I mentioned before, so the band structure for one single layer or 2 single layers of 2D materials is different, and so that happens, for example, in graphene. So the other form which you naturally get by exfoliating graphene is bilayers, and usually these bilayers are AB bilayers, so really 2 hexagonal lattices, one on top of another. And the way this is oriented is the following. So basically, AB means that the top layer is red here, the bottom layer is blue. So they're not sitting directly one on top of another, but they're slightly shifted with respect to one another. Okay, so now, because we have now 2 unit cells, 2 layers, the top and the bottom layer, we also have to take hopping terms between the layers into the band structure calculation. Usually people just take this hopping term, but other hopping terms like these here are also possible. And if you calculate now the band structure here, again around the K point, we get actually 4 bands, and the bands are not anymore linear, but the bands are parabolic. So they're hyperbolic. That means they're linear at high K, but close to charge neutrality point here, close to the Fermi energy, they're basically can be approximated as parabolic. Okay, so basically, I take this as a starting point to explain what the magic angle is. So again, we take just a single layer of graphene. We can stack another layer of graphene directly on top of it, just in the AB configuration, as I just explained. And then we can start rotating the layers. And as you can basically see, this Moiré lattice, which is formed here, basically has a periodicity which is depending on the twist angle. So if we are at a large twist angle, the periodicity is very low, but if we are at very low twist angles, the periodicity, so basically the lattice constant of the periodic pattern is really, really large. And this is sort of just to demonstrate what happens and how we think about the system, is that actually the system breaks up in regions which can be approximated by the following notation. So basically, we have regions which are brightest here, right? So these regions where basically we can approximate what happens is that we have AA stacking. So basically, each carbon atom here, so for example, here and here, each carbon atom on the top layer sits directly above the carbon atom on the bottom layer. So we can really approximate this as A stacking. Whereas in between here, at the borders, we have a different stacking where actually it is similar to what I explained about AB stacked graphene, where basically each carbon atom sits on the top, sits at the center of the hexagon on the bottom. So we can approximate these regions here as AB or equivalently as BA lattice sites. Okay, so and basically for a very specific angle of 1.1 degrees, what happens is that we end up in a situation where we have a lattice constant of the Moiré potential of 14 nanometers. So 14 nanometers is something like 50 times bigger than the lattice constant of the carbon lattice itself. And if one would sort of count up now the carbon atoms which are in one Moiré lattice unit cell, you would find that these are in the order of 10,000 atoms per unit cell. So I think, what I mentioned before, that we have a simple system to deal with only carbon atoms. I think to everybody, when they realize, okay, they have to calculate a unit cell of 10,000 atoms, that simplicity is immediately over. So it has this disadvantage that things appear to be simple. Yeah. Yeah. No. So we start with two single layers.
So not necessarily they are always bilayered.
Let me explain this point a little bit more. So basically, so we usually, when we exfoliate things, we find everything. We find single layer, bilayer, trilayer, four layers, etc. So, but whenever we find bilayer, it is always in the AB state. So because this is energetically the most favorable state for the lattices to be in, and this is how it's usually stacked in graphite. So in this lattice we cannot move anymore. So once it's at B, it's like locked to each other. We cannot move this anymore. So what we have to do is we really have to exfoliate a single layer, and then with this technique we have to basically bring it in contact with another single layer, and then try to rotate in between. Okay, so it's all done with single layers. So really like that. So we start with a single layer like this. We stamp. Yeah. Okay. All right. We stamp the second one already with a twist angle in between. Okay. Yeah. Okay. So we end up really with structure like this, and basically, if we can now try to look at the brilliant zone of these two layers, what we find is that the top and bottom layer, they're again the brilliant zones are also rotated by the same twist angle theta. And if we now look at the in the symmetry points here, then we find that actually also the K points of the two layers, they're now separated between one another. So okay, and this is basically these two K points are drawn here. So for an arbitrary twist angle, these two K points are really just represented by two independent Dirac cones. Okay, so we can start thinking about it like that. That each the top and bottom layer has independently a single Dirac cone, and if we rotate the layers close to one another, then the Dirac cones in K space are separated by this distance, basically, which is V0 times K theta. So basically, they're separated just by that region, and this is basically what's shown here. So for any arbitrary angle, so if we start just with a twist angle of 15 degrees, experiments were done on this, and you really end up with two Dirac cones, and the two lattices are just separate. So you really don't have bilayer graphene, but you have two layers of graphene which are independently sitting on top of one another. Okay, so and things really become only interesting when this distance here shrinks, when these band structures basically become very close to one another, and then they become to hybridize, as is demonstrated here. So we basically decrease the separation between the two layers, and they begin to hybridize, and eventually at exactly 1.1 degrees magic angle, these band structures hybridize so strongly that they form flat bands where the Fermi velocity just becomes 0. therefore kinetic energy is just quenched, and therefore you end up with a Hamiltonian in the system which almost has no kinetic energy, and therefore interactions start to dominate. Okay, so and just to explain this point a little bit better, right, so and just to explain this band structure a little bit better, this is sort of the single particle band structure. Again, all of this is single particle for now, so there are no interactions in the game yet. But basically, if one looks at the single particle band structure, again, this was first calculated by Bistritz and MacDonald, and also this was derived in Pablo's Nature paper. If you look at the band structure at the magic angle, then and you look at the energy in K-space, you can see that now the band structure is completely normalized, and you get these ultra-flat bands here at around energy of 0. And these flat bands, they're basically very, very flat in the sense that their bandwidth is only in the order of 10 millielectron volts. So this is extremely, extremely narrow bands. And of course, because the bands are so flat here, the density of states in these bands becomes extremely large. So basically, if I compare now the energy as a function of, the density of states as a function of energy just along this line, you can see that the density of states becomes more than 1,000 times larger than the density of states in normal graphene. So this is a completely, this sort of twist here completely renormalizes the band structure, and we end up with an entirely different system from graphene, where the bands are more than several orders of magnitude narrower, and the density of states is also more than 1,000 times higher. Okay, so, and of course, if one now takes these flat bands and one sort of calculates what happens in real space, so if we just plot the density of states back into real space, what happens is that the local density of states as a function of position on the lattice is also highly anisotropic. So basically, in the AA lattice sites, you get extremely high density of states, whereas in the BA and AB lattice sites, you have strong depressions of the density of states. And basically, you can demonstrate the whole system as a network of domain walls, where we have highly populated AA regions, which are then separated by this sort of triangular regions of AB and BA. And so AA lattice regions are the regions where the density of states is high, and everywhere else in the network, the density of states is really low. Okay, so, in principle, there exists not just one magic angle, but again, from Bistritz to MacDonald, they have calculated as a function of energy and twist angle, they have calculated W. W is basically the bandwidth of the underlying Moiré band. And basically, wherever a W becomes very small, basically in these points here, this is where this sort of magic angle condition happens and where the bands become ultra flat. And as you can see, so if one draws this, so the first magic angle arrives at around 1.1 degrees. This is exactly where all these discoveries were made. But in principle, now a lot of studies are also concentrated above the second magic angle, where, again, as you see, it doesn't look as nice from this particular model. But in principle, also flat bands are expected at 0.4, 0.5 degrees. And in principle, there are several other positions in this diagram where the Fermi velocity effectively goes to 0. Okay, and this is a video which I wanted to show is how this band structure actually evolves. So this is this was again used in Pablo's paper, and they basically calculated the energy dispersion relation for different angles. So just take a look at this. Right, it works. Okay. So basically, as you see, as the twist angle becomes smaller, the band structure flattens and flattens here at a charge neutrality point. And then at around 1.1 degrees, it becomes super flat. And then if you reduce the twist angle more and more, the band structure again becomes just weird, I guess, but not flat anymore. Okay, so and really, from this sort of calculation, you can see that really it's not like a completely discrete angle, but really there is maybe like a certain very narrow angle width at which you're expecting to see these correlations, but this angle width is still in the orders of 0.1 degrees or so. So you can be slightly off from the magic angle, but not too much. Okay, so and this is just, so this was a recent news report. So this is just to demonstrate you how much 1.1 degrees is, so how much you have to twist. So just to get you a feeling what a subtle effect this is, right? So basically when we fabricate devices, this is by how much we have to twist the top layer with respect to the other to really get this effect. And if we're off just by 0.1 degrees, we can throw away the device. We have achieved nothing. Okay, so it's really it's again with Scotch tape and PDMS, etc. It's doable, but it's still, of course, it still needs skilled hands to do that. Okay, so all right, so okay, so now just before so now I wanted to move on to show you actually some devices. Okay, so I think I already explained more or less how we stack these devices one on top of another. But there are subtle characteristics which I need to explain. So first of all, usually, so this is a typical device which is made in my group, which shows superconductivity and where we create a magic angle. And usually, what we do is we encapsulate the twisted bilayer graphene in hexagonal boron nitride, which is this insulator. So we unfortunately we cannot do this without the insulator. And usually, the device sits now on a graphite backgate. And the graphite is basically just a metal for our purposes. And what we can do is we can just apply a voltage to the graphite. Therefore, we have capacitance coupling across the insulator to the graphene. And therefore, by just changing the voltage to the graphite, we can tune the carrier density in the material. So whenever we, in our field, we say we do doping, that means we apply a gate voltage and we just change electrostatically the carrier density concentration. So this is a typical AFM image of our device. So the devices are not very large. So this bar here is 5 micrometers. So usually our devices are at best 10 micrometers long and maybe 2 micrometers wide. So I guess this is a problem for all the people who try to do muon scattering on these type of devices or neutron scattering. So really, or ARPAs even. So really the devices are ultra small. So we cannot make them on millimeter scales. So this is now transport data. So okay, so now finally I actually show some data. So this is transport data from the Columbia group, which published this paper early this year. And what we now measure in these devices is just resistance. Okay, so we just measure resistance of the device as a function of carrier density. And usually what we observe is the following. So we usually observe very strong alterations of the resistance. So for example, here at really low carrier densities, if I start with a resistance of almost mega ohms, and then if I tune the carrier density, I get regions where the resistance drops to basically 0. I get, again, resistance peaks in other regions, and then here at charge neutrality point, I get a resistance spike, and so on. So basically, if I tune the carrier density, the resistance of the device changes orders of magnitudes. And the funny thing is, we can basically characterize the device, and we can define how many electrons we have loaded per Moiré unit cell. And we can basically start at charge neutrality point here, where we basically have this resistance peak where we've loaded 0 electrons per unit cell. We can load 1 electron per unit cell, 2, 3, 4, and do the same thing at the whole side. And basically, where we find now strongest variations of the resistance is around filling -2 and filling +2. Okay, so and here, these are exactly the regions which I explained in the beginning, where superconductivity happens, where correlation effects happen, and where also the strange metal phase occurs. Okay, basically, the phase diagram which we have obtained as late 2018 is the following. Yep.
So on your previous slide, you said it's +2 and -2, but the range on the whole side is much broader. And it's more like 3 and 2. So what causes this asymmetry?
Okay, sorry, which asymmetry?
Yeah, so on your
Yeah.
top graph, you're basically saying you get a fill factor of 2 electrons or minus 2 holes, and you're saying that well, you put your gas circle around it, indicating that that's where stuff starts to happen. But when I look at this, I would say that it's more around minus 3 than plus.
Oh, so you see more happening here?
Yeah. So
Okay, yeah.
What causes this asymmetry?
Yeah, so mostly interactions. But I'll explain this data in more detail in the next slides. Okay, yeah. Okay, so basically, just to summarize, but I'll explain all these phenomenology a little bit better in the next couple of slides. But what we get is the following. So basically, if we look at the phase diagram as a function of temperature and filling, whereas filling, what we mean by filling is always the amount of electrons per unit cell. So whether we have 1 electron per Moiré unit cell, or 2 electrons, or 3 electrons, or 4 electrons, okay? And vice versa with the holes, okay? So while we start at charge neutrality, so this is the normal state of the graphene, we have typically a resistance peak here, which is just arising from this Dirac cone which I was talking about. So the carrier density goes to 0, so we have a resistance peak here. And then if we go either left or right, so if we electron dope to +1 electron per unit cell, to +2, +3, +4, at +4 electrons per unit cell, because the band structure, so because the bands are four-fold degenerate, we end up at full filling, and we get an insulating gap. So we have fully filled the Moiré band, and we end up, we basically cannot fill any more electrons in the system, and we get an insulating gap. And then, of course, if we go also to the left side, so if you fill -4 holes into the system, you also get an insulating gap. And this is all expected from single particle pictures. So from the band structure, which I've shown before, all of this is perfectly understood. So the band insulator at filling of 4 and -4, and the gap, in the resistive state at charge neutrality point, this is expected all from single particle picture. But what is not expected from single particle picture is that at filling -2 and +2, we observe correlated insulator states and the superconducting states upon doping of these. So these phases are not explained by the band structure. So these need to be now explained, taking interactions into account. Okay, so and I'll spend the next 4 slides to explain the correlated insulator state and what evidence we have that it's really a correlated insulator. And it's basically the following picture is that if we basically take just the single particle picture into account, so this is basically this picture here, and we can basically very naively we can plot the band structure which I've shown before in this sort of way, where we have here the charge neutrality point, and below the charge neutrality point we have the valence band of the Moiré band structure, and on the top we have the conduction band. And typically, if we fill up, again, to the top here, we are at 4 electrons per unit cell. If we fill up below here, we have -4 electrons per unit cell, so basically 4 holes per unit cell. And then a charge neutrality point happens where the system is at the Dirac point. So, but we don't expect from this single particle band structure any type of gaps to appear in the middle of the bands. Okay, so if we tune the Fermi energy to 2 electrons per unit cell, there should be absolutely no gap. But the gap can be explained if we take interactions into account. And this is, again, this is just like a naive picture. So, so basically, if we take interactions into account, in principle, at exactly half filling, so basically at exactly half filling of this band, or in other words, of 2 electrons per lattice site, the gap can appear if we basically imagine some picture similar to a Mott-like insulator. So the picture is the following. So we could have a lattice like this, where we have 1 electron per lattice site. But in principle, at this point here, the conduction should be just metallic. But because we can take interactions, basically Coulomb interaction between different electrons and different lattice sites, these Coulomb interactions, in principle, can stop the conduction. They're basically electrons repel each other and don't allow for the next neighboring electron to hop to the next site. And therefore, such a Coulomb interaction, in a Mott-like picture, would lead to an interaction gap like this. And these type of gaps you only expect at integer values of electrons per unit cell. So you cannot have this type of gap arising at an arbitrarily filling, but you really expect this gap to arise exactly at an integer filling of electrons in the band. Okay, so basically this brings me back to the transport measurements. So again, as I just try to repeat, so basically at this position here we have a band insulator, here we have a band insulator, here now we have 2 electrons per lattice site, and we also observe an insulator. And also here at exactly minus 2 electrons per lattice site, we also observe an insulator. And we are sure that these are basically gapped states because we actually can measure temperature activation at these. So we fix a Fermi energy at this state, and we can just measure the conductions as a function of inverse temperature. And because of any energy gap, should give you some temperature activated behavior. Just for this expression here, we can actually find that we can fit the temperature dependence in these states with this exponent here, and we typically find that the gap at filling factor -2 is in the order of 0.34 MeV. The gap at filling factor +2 is in the order of 0.37 MeV. So basically, all of these gaps we can characterize pretty well with transport, and we can actually really show that, unlike expected from a single particle picture, these gaps are really sharply pleasant. And that being said, if we just tune the system, as I showed here, if we just tune the system slightly left and right from this integer filling, again, the system recovers just normal metallic behavior, and there are no gaps, no sort of weird interaction effects happening there. Okay, the other sort of evidence which we have right now is also from STM. So currently there are really just transport results on these systems, and also the second type of experiment which is performed right now is STM. So with STM, they can actually do a much more controlled job to studying these effects. So basically, they can just apply a tip to twisted bilayer graphene, and through the tip and a gold contact, they can just measure the current very locally in the sample. So and this is, for example, a typical STM height map, which they can perform on twisted bilayer graphene. So they really find that these AA lattice sites have enhanced conductivity than the AB lattice sites. But of course, they can also take spectra, and they can sort of measure the local density of states in the system. And indeed, they can find that in these AA lattice sites, they can have enhanced local density of states, just in a similar picture which I explained in the beginning. So really, this whole twisted bilayer graphene breaks down in this Moiré unit cells with very high local density of states. So what they can do now is they also can apply a gate. Just as we do in transport, they can apply a gate, and they can basically sit at the AA lattice site here, and they can look how the spectrum changes. So and this is typical results they get. So this is, again, local density of states is a function of energy, and usually the blue curve is the results people obtain in several experiments right now. So they obtain basically the really high density of states in the Van Hove singularities, which are created by the flat bands. So basically, each of those peaks here is just basically the extremely high density of states which arises in each flat band, and the valence and the conduction band. But now, since we can tune the filling factor, we can tune the gate. What people have done is they have zoomed into one of those bands. So basically, they have zoomed into this AA lattice site here, and they have filled the system to a filling factor of 2. And as you can see, really from STM spectra, they can observe a gap exactly at filling factor 2, which is, for example, not present at filling factor 2.4. So again, this is direct evidence that there is an energy gap forming in exactly at filling factor of 2 and not in other filling factors. Okay, so this is really, I think, so far the best evidence that locally we have these interactions kicking in. Okay, so how much time do I have? Still, so, okay, all right. Okay, so then the other thing is, of course, what about superconductivity? So I think, yeah.
Question here.
Yeah.
So what you see is when you go away from this filling, I mean, you okay, you have this gap,
Mm-hmm.
and then in the vicinity, I mean, you have enhanced local density of states.
Right.
I
Mm-hmm.
mean, in STM now, when I just look at the measurement,
Right.
I would expect that you only see the metallic states, right? So the conducting states. If you have a mud insulator,
Oh, so okay, I see. So you mean why this never goes? Why it's not a hard gap?
yeah.
Why it doesn't go to 0? Is that the question?
The
yeah.
question is also what the physics is in the bumps behind. I mean, usually when we think of the mud insulator,
Right.
for example, we say that the quasi-particle MP that
Mhm.
is at the Fermi level,
Mm-hmm.
it goes down, and then you have just the incoherent Hubbard bands.
Right. Right.
But the incoherent Hubbard bands are essentially localized states.
Right.
So they are not conducting.
Right.
So they should not be seen as a local
Right.
density of states
Yeah.
in STM. If the physics here is also that of the mud insulator,
Right, yeah. Yeah.
I'm just wondering whether this is how to interpret these.
Okay. Yeah. So right. So I think so. The history of what these interactions are, the history of what this ground state really is following that in his original paper, Pablo wrote that it's a mod-like state based on the arguments I tried to present. But I think right now nobody really supports that mod insulating picture, and people just like more generally say it's a correlated insulating state. So basically, at this point, we don't know. Again, there are just less than 10 experiments done at this point in time. So only transport and only STM at this point. And sort of, this picture which I was drawing, this is again just to make sort of an overall intuition work here. But this is not something which we know yet. Okay. So I think everything we interpret in this field at this point has to be taken with a grain of salt. So I think what I can confidently say is that in transport we see gaps at integer fillings. So we can say that. Then these gaps are also appearing in STM, whereas again in STM they don't show a gap which completely goes to 0. They haven't measured the temperature dependence of it. But what they can say is that this gap really seems to appear only at integer filling, and this gap also does not exist in devices away from the from the magic angle. So when you create when you create a twisted bilayer graphene system at 1.3 degrees away from the magic angle, where even from the single particle picture you don't get flat bands, you're not expecting interactions. They're not seeing this type of dip. Okay, so this is sort of so this is the evidence which we have at hand right now that something is going on. It smells a little bit like a mud insulator, but we wouldn't call it anything yet. So I think the word which is broadly used right now is correlated insulator. Okay, but it doesn't go to the microscopics of it. What's really happening there? Okay, so right, so this is again, this is just the evidence that really at integer fillings of the unit cell really people observe some sort of gaps appearing which are not supposed to be there at in the single particle picture. So the intuition tells us that it could be interaction-driven gapped states. But of course, you will find on any of these topics 1,000 theory papers at this point. And I think we're not actually close to a conclusion. So we're actually really just in the beginning to amount some experimental evidence. So the other thing is that as I mentioned before, so if it probably takes a little bit of time to read all those color plots, but this is all we have right now. So basically, the other thing is that this mod state, and again, this is still from the paper, so people don't call it mod anymore. Okay, so this is published in the paper, so one cannot remove this anymore. So this correlated insulating state, which is here red in this color plot, and red means just very high resistance, whereas blue means very low resistance. That mod insulating state sits at half filling, so this is basically a filling, half filling or a filling of 2 around here, around 1.5 times 10 to the 12 centimeter per squared. And as you can see, if we now apply a gate and change the carrier density slightly beyond this correlated state, if we move here or here, then regions of really low resistance arise, okay, which is dark blue. And in principle, this resistance really goes to 0. So and basically, this is data from again from Pablo's paper. You can really see that if we zoom in into these superconducting domes, if we sit at optimal doping at the point where the superconducting TC is the highest, we can really go get curves where the resistance goes to completely to 0 with temperature. Okay, so basically, the reason why we call it superconductivity is primarily because we observe a 0 resistance state, and and this is as expected from superconductivity. And the other thing I want you also to pay attention to is that really the resistance at high temperature really follows this linear temperature dependence, as probably is familiar to you, to many of you, and is debated right now whether this is a strange metal phase, for example. Huh? Me? No. So yeah. So let me go through the experimental evidence we have that it's superconductivity, and then I think one can discuss further experiments, because right now it's really just transport which have shown superconductivity. Okay, so from transport we can measure resistance. Resistance drops to 0, feels like superconductivity. Then, of course, the other thing one can do is one can apply a perpendicular magnetic field, and one can see whether this superconducting state disappears. And indeed, so this is again resistance as a function of temperature for different magnetic fields, and as you can see, at 0 field really resistance goes to 0, but then at perpendicular field in the order of 100 millitesla, this superconducting state disappears, and really sort of metallic temperature dependence is recovered. Okay, so and basically from this data one can extract the critical field. Again, as in perpendicular field, one can really see that the critical field we can extract as a function of temperature follows the Ginzburg-Landau theory. So this basically this linear temperature dependence, which disappears at Tc, and basically also from this relation we can extract from this magnetic field dependence we can extract the coherence length of this state, and we usually find something in the order of 30 nanometers, but I would say it's usually always a few lattice constant of the Moiré, so it's usually 2 or 3 lattice constants. Okay, so that's another evidence that this looks like superconductivity. Then, of course, we can perform nonlinear conductance measurements, so we can basically look at the IV characteristics of this state. And indeed, we observe really a zero resistance state here, where by changing the current, we don't change the voltage drop across the sample. And then at a certain critical current, I see really this state becomes resistive again. And here also, this looks very much what you expect from IV characteristics of a superconductor, where again, one can show that something like an IC exists. And furthermore, because it's a two-dimensional system, we can also show that this sort of transition here is extremely, extremely sharp. And we can show that it's sharper than I to the third. So this also suggests that it's really two-dimensional type of superconductivity, which is also consistent with a BKT transition. Okay, so this is most of the evidence we can obtain with transport. But then probably the most convincing evidence so far is the following graph. Okay, so this is basically a Fraunhofer type measurement, again done by Pablo. And basically what happens here is that, you know, what I haven't mentioned is the system is inhomogeneous. So in principle, this whole twist angle, it's not completely homogeneous across the entire size of the device. So you might have regions which are close to the magic angle, but then you might have pockets in the sample which are away from the magic angle. So in principle, you can get phase separation in the system, so you might end up with sort of inhomogeneities, where some regions are superconducting, some are normal metal, some are superconducting, etc. So surprisingly, when Pablo was just walking around the phase diagram, changing N and changing magnetic field, they see regions which look like Fraunhofer pattern, where basically this resembles SNS junctions or Josephson junctions, where basically phase coherent transport can happen across a weak link. And really, these type of Fraunhofer patterns are usually ample evidence that there is a quantum coherent state, which really I think is hard to explain other than with the existence of superconductivity. And that brings me back to your question. So this is all the evidence we have. Okay, so I think I've pretty much every time I discuss with somebody, there's people from different communities who ask me for another sort of striking evidence for superconductivity. So far, I think everybody's asking Meissner effect. Of course, you know, with these samples, again, they're 2 by 10 microns small. Okay, so basically, the only way you can measure magnetization in these is with a nanosquid. Okay, so and these experiments are underway, but you know, these are very difficult experiments. They take time, and I probably expect something to happen next year. So probably next year we'll get these experiments underway. But you know, with all the traditional techniques which we have readily available for you know, bulk superconductors, a lot of these techniques are just not applicable here. You know, so we have to be a little bit inventive, because it's really just a two-dimensional material, very small, and yeah.
You mentioned Josephson junctions. Is it even realistic to think about how you might couple two stacked bilayer graphene systems together, or what you'd have to do? Because one of the edges is twisted, and so you have the interface might not be very clean there to actually couple them together. You wouldn't certainly be able to twist the graphene very well, right?
Right. So by the way, this is an intrinsic Josephson junction, right? So it's all graphene here, right? So this is, so one way, for example, to improve this experiment, again, this is a phase separation which happened randomly, but one way is, for example, to make a local gate where you just can tune the center of the magic and graphene. You can tune that into correlated insulator phase, and you keep the rest superconducting. So just by having like a local gate geometry, you could actually repeat this experiment in a much cleaner way, and people are trying to do this right now. But this is early on in the field again, so I would also expect it to happen in a year or two, so where one can really make controlled experiments. The other thing is, I think, which people take as ample evidence for superconductivity is heat capacity. So if we could measure heat capacity here, that would probably add to the story. Again, nobody has ever measured heat capacity in graphene. Okay, so because it's such a small system, so the traditional techniques which are used for bulk superconductors would just not work here, because the heat capacity of the thermometer which you use would have a bigger heat capacity than the graphene itself. So novel techniques have to be developed. I think neutron scattering, muon scattering is also going to be very hard. So people are trying ARPAS right now. ARPAS is really hard. Okay, so right. So I think some of the sort of obvious experiments one wants to do superconductors will just take time here. Will not happen the day after tomorrow. Yeah. 2 by 10 microns, so like 20 microns square. Okay. Right. Right. So this is pretty much the end of the talk. So I think I'm happy to discuss much more and maybe explain some of the experiments more in detail. What I want also to end up with is I want to emphasize that really this field is really currently, as of the last couple of months, started to also evolve away from just magic angle graphene. So for example, a recent study here by the Harvard group, they have shown that you can do the same trick by twisting bilayers on bilayers. So instead of twisting a single layer on a single layer, you twist 2 bilayers on top of one another, so these bilayer graphenes, and you get a very similar phenomenology. You also observe correlated states, and you also, people think that they also observe superconductivity. So this magic angle trick also works for bilayer. It should work for tri-layer. It should work for, yeah? Yeah, so the top is an AB stacked graphene, and the bottom layer is AB stacked bilayer graphene. And you could do this with tri-layer stacked on tri-layer, 4 layers on 4 layers, I don't know. So you can, but then there's also a lot of studies right now where people try to make single layer on single layer on single layer. So like a tri-layer where every part is rotated and things like that. Then what people have also looked at was HBN-aligned magic bilayer graphene. So as I mentioned, HBN is also a hexagonal material. So in principle, you get this Moiré pattern between graphene and HBN. So in principle, people have already observed also similar correlated insulating states in a system where HBN creates a Moiré potential on magic angle bilayer graphene. So it's like, again, a triple rotated system. So these Moiré patterns can become very, very difficult. Then another recent effort was in HBN-aligned ABC trilayer graphene. So this is now not AB. So this is now trilayer graphene, where similar to AB bilayer graphene, now three layers of graphene are on top of another in this ABC type of stacking order. And if you again align it with HBN and create a Moiré lattice, you can also get correlated states and superconductivity. So somehow, surprisingly, this sort of picture of these flat bands and interactions giving rise to correlated states and superconductivity, it somehow seems to be universal across many different systems. And also now talking about non-graphene system, there are also studies underway where people created, for example, these TMDs, transitional metal digital collagenide, which are usually semiconductors, where I think what I know from just communications is Columbia and Harvard, they, for example, stacked 2 WSE2, so 2 semiconducting 2D materials, also with the magic angle on top of another, and they also seem to see similar type of behavior. So in principle, so it's really the field is also shifting to many other exotic systems, and it looks like there are a lot of different combinations which are possible. Okay, so I think I'll end with that, and I'm happy to answer more questions.
For this stack by graphene,
Yeah.
qualitatively, do the results sort of improve in terms of measurable quantities?
Right. So there's several improvements. So it's actually easier to get a magic angle in these. So somehow this sort of, you don't have to line it on 0.1 degrees precision, but now with 0.2 degrees precision. So it's easier to get it. TC went up to 6 Kelvin. So in the case of twisted bilayer graphene, it's around 3 Kelvin now. So in Pablo's paper, TC started at 1.7 Kelvin. So we actually, I will talk next lecture, we increased it to 3 Kelvin, but in bye-bye it's now 6 Kelvin. But it's not entirely sure yet if it's a real superconducting phase, so this is still under debate. So these papers are going through review right now, and as I hear, some groups see this superconducting phase, some don't, so there's more debate about this superconducting state. Right.
You have many Moiré systems,
Yeah.
depending on the angle
Yeah.
of protection. Is there any systematic determination on how the phase diagram changes when you change the type of Moiré? That is there a correlation between the phase diagram and the periodicity of the Moiré that you get?
So let me try to, yeah.
Working on the same always?
No, I mean,
That the 1.1 degree always?
So I think so. Let's see. So I think so I have to, just before I maybe try to answer your question. So I think the statistics is very low in the system. So I think this is like one device which was reported. This is maybe two or three devices. So we don't, right? Yeah.
Of the simple two-layer
Yeah.
case.
Okay.
In this case, you could have different angles giving different Moiré.
Right.
So how does that evolve? Is there any systematic study of that, or
So
one focused on one?
so there is. You will so right now it's all about magic angles. So it's all about the first magic angle. So it's all around 1.1 degrees. We have now also a study coming up about the second magic angle, which is around 0.5 degrees, and we can say that we really see flat bands, many flat bands actually arising at the second magic angle. I think most groups in magic angle graphene concentrated, however, on the 1.1 degrees. And because there's still a big uncertainty in the device fabrication, you end up with a huge variety of different angles in the end of the day. So probably, again, Pablo from MIT, Pablo Herrero, he has the most statistics. I think he measured 10 devices which were superconducting. And he can say that really, as a function of twist angle, TC has also a dome-like shape. So basically, he would, can I draw something here? Yeah. So I'm not allowed to draw here, right?
You are.
Yeah, okay. Okay.
Just turn on the mic.
So basically, if one draws TC as a function of twist angle in magic angle graphene, then you would get something like a dome shape where max TC of around 3 Kelvin is at 1.1 degrees, but you still get signatures of superconductivity at 0.9 degrees, okay, and you still get it up to 1.2 degrees. Okay, and with correlations, it's actually slightly different. Again, this is not published. This is just what I know from discussions. From correlations, correlations really seem to seem to have some sort of shape like this. So this is again, and then they disappear at one point. But interactions actually around magic angle, they're not the strongest. They're somehow stronger even on the sides of that diagram here. But yeah, the statistics is very low. So I think overall, I have to say, so probably in magic angle graphene, we are talking about 12 devices which were measured among 5 groups or so.
Can you remind us what is the lattice mismatch between HBN and graphene, if there is one?
Okay. I don't have a picture. So okay, so basically, let me go back all the way back. Okay, so basically, so in graphene, in order to get this Moiré periodic potential, you need to misrotate them with a certain twist angle. Okay, but in HBN, again, HBN has the same hexagonal structure as graphene. HBN has, however, a slightly different lattice constant. So in that different lattice constant always gives you a Moiré lattice, which looks exactly like that. But even if you don't have a twist angle in between. So if you perfectly align graphene on HBN, you would get this Moiré potential on graphene and HBN. And, right. Was that your question? Or? Yeah. Yeah, and you, yeah, no, so yeah, so, but it's basically, yeah, you can think of, I think you can think of just this here. You get really, if you put graphene on HBN, you get some similar Moiré potential. But the other thing I want to say is that really a lot of people are playing around with really PowerPoint right now, trying to put as many layers as possible, and it's pretty cool what kind of different Moiré structures you get. So if I would put a third layer, then you would have certain variations here and there. So it becomes really complicated very quickly if you put in. So if twisted bilayer graphene with 1.1 degrees is not difficult enough, then you can put another layer of HBN and rotate it more. So degrees of freedom that's why reproducibility is so low at this point, because they have so many degrees of freedom. Yeah.
A question about the intrinsic Josephson junction
Yeah.
that you showed. Like, what causes this change in angle in the single sample?
Yeah,
So
right.
clean and everything,
Yeah. So so graphene is clean. In principle, one can say that. So, however, the strain in the system in the way we fabricate these devices right now can vary locally a lot. Okay, so it's more like a strain variation along the spacing of the device. And then, yeah, if you can imagine, I'll probably discuss on Thursday a little bit more about it, but you can have a slightly different strain in one end of the system than the other, and what the strain does, it just, if you can imagine, if you stretch that system a little bit, then it becomes very different. So what we think is the main source of disorder in graphene is twist angle and homogeneity. So it's not impurities, it's not defects, it's really strain effects and this type of stuff.
So I think you showed a phase diagram as of late 2018.
Yeah,
So what is the latest consensus on the phase diagram?
right,
So for example, I think there might be insulating state on
right. Okay, right, so, okay, so you see the stars here, right? At +1, +3, right. So, so that's not again, so this is a phase diagram of late 2018. What I will discuss on Thursday is our latest work where we actually observe insulating states at every integer filling. So at +1, +2, +3, and -1, -2, -3. And we also observe superconducting states around these as well. So in principle, this sort of correlated insulator story and this whole phase diagram has to be extended to the other integers as well. And along these lines, also the sort of questions which are being debated right now is the role of symmetry breaking in these different states, because again, so filling factor 2 means 2 electrons per Moiré lattice site. So that means that these 2 electrons can be spin up and form a spin singlet, but also they could be also spin polarized, but they're in different values, right? So so this is a debate, and of course for these integers of filling, so if you have 1 electron per unit cell, then of course both spin and valley have to be degenerate. Have to be broken, and then of course you also might add up in ferromagnetic states and things like this. So in these states, really a lot of the stories which are developing is that people observe ferromagnetism, people observe topological states and things like that, and then this I'll keep for the day after tomorrow.
Perhaps one last question. Okay, maybe it fits kind of an open question.
Okay.
So can you maybe go back to this slide with these different stackings?
Okay, the last one.
Yeah, right before the flat
Yeah.
ends, right?
No,
Somewhere.
at the beginning. Okay.
So, yeah, this one.
This one.
So when I read up like theory papers,
Yeah.
that often try to like build some effective models for this, and then they either try like this triangular lattice or this hexagonal lattice.
Okay. Yeah.
Right? Is there from the experimental kind of view are some rule of thumb which materials are actually better described by this triangular structure and which one by the hexagonal structure?
Experimentally, I wouldn't.
Okay, so they are not
No.
rules or something.
No. So most I have to say most of the. No, I don't think experimentally. I don't have any. Yeah, I know from a lot of theory papers the starting point could be a triangular or a hexagonal lattice, right? Yeah, from experiment we just stack 2 graphene on top of another.